Esther, Mario Gleirscher, Jonathan Huerta, and Georg Struth on hybrid systems verification with Isabelle HOL, simpler syntax, better models, faster proofs. And the talk is going to be given by Jonathan Huerta. The floor is yours.
Thank you. So, yeah, so we achieved simpler syntax, better models, and faster proofs, and this we did in our hybrid system verification framework, which we formalized inside the Isabelle HOL proof assistant. So, as people have seen in this session, our objective is to increase confidence in the correct integration between discrete controllers and physical systems. As an example for this talk, I brought the water tank, where we want to ensure that the level of water in a tank is within certain boundaries. And to achieve this, the controller takes some measurements, and based on this, it decides whether to turn a water pump on or off, which in turn sends an inflow to the water tank, and that changes the level of water in it. So, and to guarantee that this is, to increase our confidence in this integration, what people do is that they do formal models and describe everything mathematically. So for example, the level of water in the tank is the rate of change at which it changes. It's a differential equation. And the fact that the level of water requires to be within certain boundaries, it's modeled with inequalities. Also, the program that the control implements is a model of what the system should do. And then we can take this one step further and consider the differential equations as if they were another program, and sequentially compose it with our discrete control. And this we put inside a finite iteration, so that we're effectively saying that the control is intervening and then letting the physics unfold. Whenever we have these integrations between discrete controller and continuous dynamics, we have what is called a hybrid program. And the great thing about hybrid programs is that we as formal people can place it inside partial correctness specifications like HOL triples, or formulas from differential dynamic logic, and then we can make statements saying that if the system starts satisfying certain precondition, then after the execution of the system, we'll end up in a state where a post condition is satisfied. And usually, well, in this case, the precondition and postcondition for our tank are the same. And whenever we have this coincidence, we call that an invariant of the system. So yeah, we do these formal methods on paper, but then we would also like to mechanically check that these implementations are correct. And for that, we have proof assistants. And as a little teaser for what we have achieved after our work in this paper, I wrote a formalization of the water tank in the Isabelle HOL proof assistant. And you can see here is this is a HOL triple where we have a loop where we have first the control and then the differential equations where they change according to whether the water pump is on or off. And also, thanks to our contributions in this paper, we just need to supply some local facts about the inflow and outflow rates being positive, and use our automatic tactic from Isabelle to verify that this simple hybrid program satisfies this specification. So how did we achieve this in this general purpose proof assistant? Well, in previous work, what we did is we had this verification framework, and the steps to obtain this verification framework are 4. So first, you have to formalize an algebra of hybrid programs, like a Kleene algebra or an algebra of predicate transformers. And what this algebra provides to you is a model for the operations between programs, and also a way to model programs themselves. Then you also formalize the semantics of the algebra, because this allows you to write even more programs and also to check the soundness of the actions of your algebra. And in this case, we chose to model programs as functions from states to a set of possible output states. That is a non-deterministic modeling. And this allows you to add assignments and differential equations to your model. Then you have to formalize the elements of your state space, and this is going to be the main topic of this talk, so I'll skip it for now. And after that, what you have to do is formalize the rules of inference of logic, and also prove the soundness of this inside the general purpose proof assistant. And what this generates is that you obtain verification workflows with the proof assistant. So for instance, we currently have 3 workflows. The first one, when you want to check that certain differential equation satisfies a given specification, well, users, or they can use a computer algebra system or to supply us a function that is the solution candidate of the system of differential equations. And then Isabelle certifies that this is indeed the solution. Alternatively, if you do not have the solution, you can also do reasoning in terms of invariance, as in differential dynamic logic, where you reason about the system of differential equations and do not provide any solutions explicitly. Or also, if you are lucky enough to have the dynamics specified in terms of time, you can write them directly in the specification and also prove that your HOL triple holds. Now, our objective for this paper was to turn this framework towards a formal method, and for that we decided to start on the program store model. And so that's made our contribution. So we have a more refined hybrid store model, which is based on an algebraic entity called lenses. And lenses are very generic. We have formalized lenses in Isabelle HOL, and we can use these lenses as a hybrid store model for other shallow embeddings in Isabelle, not only for our verification framework. And on top of this store model, we have built a user-friendly specification language, and this provides cleaner syntax to our verification framework. And of course, because this is done on top of the lenses, this can also be exported to other shallow embeddings in Isabelle. And furthermore, because lenses are very generic, they allowed us to think about the state space of hybrid programs more detailedly, which also allowed us to prove more inference and calculational rules. So for instance, we now have more rules about derivatives, framing conditions, and we even were able to prove the differential Gauss rule from differential dynamic logic. And also, because we have these rules, we can supply them to our tactics in Isabelle and then obtain better proof automation. All these developments are available in our online repository. And for the rest of the talk, I just like to explore how we achieve this in more detail. So as I said, we start with a hybrid store model based on lenses, and the key takeaway from lenses is that we're going to use them in 2 ways. In the first, we model variables with lenses, and that's a very common application of them, because lenses provide an accessing and unmutating function, where the accessing function takes a given state and gives you the value of the variable that you're analyzing with the lens. And the mutating function takes a given state and a value and gives you an updated state. The other view that we are going to use for lenses is as a projection to a subpart of the state space. Basically, the accessing and mutating functions allow you to look at certain part of the state space, and we'll see how we achieve that later. So for the first application of lenses as variables, we'll build a specification language. So we use Isabelle syntax translations, where the left-hand side is what the user would write or read, but the right-hand side is what Isabelle would interpret internally. So for instance, with this simple expression where x and y are lenses or variables and z is a constant, Isabelle would automatically translate it into this expression with the accessing functions internally. To have some code snippets for you, we have this. This would be what the user would input, and then Isabelle would tell the user, well, you have just input this, where y and v are lenses, and this is signaled with these dollar signs. But internally, Isabelle would process this expression as an expression where you have the accessing function replacing every dollar sign. Now, for the second application of lenses, we consider them as projections to a part of the state space. And for that, I brought an example. Take a function from the state space to the state space and take a subpart C of the state space. And then with the accessing and mutating functions, you frame this function by type coercing it so that you obtain this new type. If you inspect mathematically what this new type is doing, because C represents a subpart of the state space, then if you provide it with a given state, then this function becomes the restriction of f to that subpart of the state space. And also, if this C is the continuous part of the state space, that means it's for example, if C represents a vector space, then we have a function from vector space to vector space, which is a vector field, and that's the representation of differential equations. What this allows us to do is that we can now have a larger state space where we talk about a subpart where the differential equations lie. And we can take this idea further to other domains. So for example, we formalize also a framing rule as in separation logic, where we say that if a hybrid program does not modify a certain region of the state space described with a collection of variables, and these variables are we can freely substitute them in a predicate, and this hybrid program satisfies a HOL triple, then we can safely conjoin the predicate to the precondition and postcondition because the program is not affecting the predicate. Also, because now we're talking about a subregion of the state space, we obtain some derivative rules in that subpart. So for instance, we obtain the traditional ones like linearity and the Leibniz rule. And as I teased before, we were also able to formalize, thanks to this framing use of lenses, the differential Gauss rules of differential dynamic logic, which basically says that a given predicate is an invariant of a system of differential equations if we can extend that system of differential equations with a new fresh variable that satisfies certain conditions. Now, for a quick view of how we do this in Isabelle, we implemented this data space command, which is just an Isabelle local, but with the added benefit that you can explicitly tell Isabelle which ones of your terms are going to be lenses, and Isabelle automatically provides well-formed properties about these variables. And then for the first workflow, what you would do is you formalize the system of differential equations, you formalize the system, the solution to the system, which can be provided by a computer algebra system. And then you just check that that satisfies the conditions for, that the system of differential equations satisfies the conditions for uniqueness, and that the solution given is in fact the unique solution to the system of differential equations. And as you can see, for this simple example, like the Huerta, this is fairly easy with our automated tactics. Alternatively, you can also use invariants, and again, we just use our tactics that use all these derivative rules that I showed in a previous slide. And finally, if you want to do this in one go, you just formalize the control, the dynamics of the system. You place them inside a loop, which also is inside a HOL triple. And then you just call some local facts and our tactic for manipulating HOL triples and weakest level preconditions. And also you call the fact that the solution satisfies the given system of differential equations. The other proof of this system as invariance is the one that I showed at the beginning of the slides. And finally, well, I've shown you how we achieve simpler syntax and faster proofs. And that was because we have this new hybrid store representation based on lenses for our verification framework. But this hybrid store representation, you can port it to other shallow embeddings in Isabelle. Now for future work, our specification language, we would like to change it so that it resembles more closely Modelica or Mathematica, so that these systems can supply solutions and invariants to Isabelle, and then Isabelle just is just needs to certify the inputs from these systems. And after that, because Isabelle provides the possibility of code generation, we would be interested in seeing if we can do code generation of our verified controller implementations. And theoretically, we're also interested, well, if we were able to absorb some rules from separation logic and differential dynamic logic, which other formalisms about hybrid systems we can incorporate to our verification framework. Again, you can see all of this in our online repository, and you can send questions to this email. Thank you very much.
Thank you. Question time. Anyone, either by raising your hand or
I think Andre is raising.
Andre has his hand up, and it's a new hand again. Yes, go ahead.
Thank you. Very nice talk. There's two things I would like to understand in more detail. The one is the question you talked about, like reasoning techniques like differential ghosts and so on. But in your examples, you mostly talk about constant differential equations. Is that what most examples that are actually proved usually work like, or is this just a matter of simplifying for the slides?
Yeah, this example was just a simplification for the slides. We used in the paper, we used the differential ghost rules to prove the canonical example for differential ghosts, which is the differential equation where the right hand side is the negative, the minus the left hand side.
So x equals minus x. All right.
Yeah. X prime equals minus x, and we prove that using our differential ghost rule. Yep.
My other question is about the differential ghost implementation that you have there. What struck me is that your rules seem to me fairly complicated, which is maybe just a matter that I'm not familiar with your notation yet. And in differential imaging logic, differential ghosts is actually one of the easiest things to write down. So I'm trying to understand where that comes from. Is that a consequence of the fact that differential imaging logic is working with uniform substitutions to work syntactically with these kinds of changes, and you're going in the semantic route, or where exactly does this come from?
Yeah, exactly. Because we're talking about the semantic route, we need to be explicit on how our variables interact. And that's why we have to specify here that our new fresh variable is independent of the other variables in the system of differential equations. And also it's not affecting certain part of the boundary conditions.
And the sharp means what exactly?
It's an on-restriction predicate. If I've always confused, so it basically means that it's either that y does not freely